Hi, I'm Hense.
And I'm Trevor Pfeil. This is our recap video for Wednesday's lecture. So in last Friday's lecture, we covered Euler's integration method to estimate higher order differential equations, and we covered some of the errors that can produce. And so what we're looking for and what we looked for in class on Wednesday was more accurate methods of estimation. And the first way we looked at that was with the modified Euler's equation. And all that is a single term expansion of the Taylor series that Euler's original equation is based off of. And so that expansion gives us a second derivative here, which we can't quite use because we're chasing a system of only first derivatives, a first order differential equation. So using the definition of the derivative here, we can convert this second derivative to a function of only single derivatives using the slope in the current time step and the next time step. But the issue is we don't know how to solve for the slope in the next time step yet. So how do we do that? The first step is we know that the slope in the next time step is obviously just a function of the time value and the y value that it's at. So using this equation here and substituting into our modified Euler's equation, we can simplify this down to a system that only has y's and t's in our current time step. And we know how to calculate those based on the same methods we used for the original Euler's equation.
After we discussed the modified Euler's method, next we started talking about the Runge-Kutta method. Now we didn't go too much into the derivation of this in class because it is very complex, but the nice thing about it is it's also much more accurate than the Euler's method. So it's understood that our y sub I plus 1 is this equation with these four constants for an RK4 method. And these constants are each follow a very similar pattern where you have the delta t, your time step, multiplied by your derivative function. And for K2 and K3, you have your derivative function with y sub I, but K1, which is the previous constant in each of these terms. The last thing we talked about Wednesday was numerical errors for these various types of numerical integration systems we talked about. The four errors are truncation, step size error, which are the same thing, round-off error, instability, and stiffness. Now, step size error is when your step size is too large for the given problem, so the method is actually much less accurate than it would be if you did an exact integration. Next, we have round-off error, which is the error that occurs if decimals are cut off or rounded in a computer system. And when they're accumulated over a long period of time, you actually get instability within your system. And then the last one is stiffness, which basically talks about step size error and how if you have a high frequency system, you're going to need a much smaller step size to make that approximation accurate than if you were to have a larger, more curving system, then you would need a larger step size.